Move to problem number 2. Problem number 2. A reciprocating compressor draws in 500 cubic feet of air whose density is 0.074 pound mass per cubic feet and discharges it with a density of 0.304 pound mass per cubic feet. At the suction, pressure 1 is equivalent to 15 psia. At the discharge, pressure 2 is 80 psia. The increase in specific internal energy is 33.8 BTU per pound mass, and the heat transferred by cooling is 13 BTU per pound mass. Now, determine the work in horsepower, neglecting the changes in kinetic energy. The given are, we are going to, just like what I did in the previous problem, I am going to divide my problem into two states. So density 1 equals 0.074 pound mass per cubic feet, and then density 2 is equivalent to 0.304 pound mass per cubic feet, and then my pressure 1 is equivalent to 15 psia, and then my pressure 2 is 80 psia, and then the change in specific internal energy, it increases to delta U is equivalent to 33. It is positive because it is increasing or increases to a certain value, so that's why the sign convention is positive on mass. And then the heat transferred by cooling, so the keyword here is cooling, therefore the sign convention, the sign of our heat is negative 13 BTU per pound mass. Since it is per unit mass, therefore this is specific heat. Specific heat transferred, because specific heat is different from specific heat transferred. So those are two different things, so let's not get ourselves confused. Now our main goal is to determine work wherein change in kinetic energy is negligible or equivalent to 0. So the next thing that we would do is we are going to draw our system. Since elevation on both sides are not given, therefore our system looks like this. Just like this. Like that. So both ends are leveled or has the same elevation. So you will always assume that they are on the same elevation unless it is specified that they are different in elevation. So since their elevation are equal, so therefore our change in potential energy will also be equivalent to 0. So now let's proceed in solving our problem by writing down the general energy equation. So energy equation is potential energy 1 plus kinetic energy 1 plus U1 plus EF1 plus Q is equivalent to PE2 plus KE2 plus U2 plus EF2 plus work. Just like that, and then we are going to transpose everything else to the other side and retain our work since we are solving for our work. And now work is equivalent to potential energy 1 minus potential energy 2 plus kinetic energy 1 minus kinetic energy 2 plus U1 minus U2 plus EF1 minus EF2 plus Q. So this is our general equation in solving for work. Since potential energy 2 is constant, or the change in potential energy is negligible, so this will be 0. And then also the same thing with our kinetic energy, this will be 0. So we are left, in solving our work, we are left with internal energy 1 minus internal energy 2 plus EF1 minus EF2 plus our heat. So these are the variables that we are going to work or find in order to solve for our work. So in solving internal energy 1, internal energy 2, we are going to base it to the given the change in specific internal energy. So the change in specific internal energy is equivalent to specific internal energy 2 minus specific internal energy 1, just like that. But the equation here is u1 minus u2, not u2 minus u1. So what we are going to do is we are going to transpose the negative sign to the left. We are going to factor out the negative sign. So negative u1 minus u2. So this is so-called formula transformation, just like that. And since this is specific, in order to make this one into internal energy, not specific internal energy, we need to multiply the specific internal energy, change in specific internal energy, by our mass. That's why we need to solve first. Since we don't have a value for our mass yet, let me just show the general equation that we need to. So u1 minus u2 is equivalent to negative internal energy 1 minus internal energy 2 times mass, or mass. We know that negative u1 minus u2 is equivalent to the change in internal energy. So we are just going to substitute this one with our value, which is 33.8 BTU per pound mass. Now, the only thing that we need to do is to solve for our mass. So solving for mass, we have a given volume. Let me just input it here. Volume is 500 cubic feet per second. So mass 1 is equivalent to mass 2, so we can solve for our mass by using density 1 as our clue. So density is defined as mass over volume. So solving for mass 1 is equivalent to density 1 times volume, and our density 1 is given 0.074 pound mass per cubic feet multiplied by our volume, which is 500 cubic feet per second. So cancel cubic feet, we are left with pound mass per second. So mass 1 equals mass 2 is equivalent to 0.074 times 500. So our mass flow rate is 37 pound mass per second. So this is our mass flow rate. So solving for u1 minus u2, we're just going to multiply 37 pound mass per second to the value of our change in specific internal energy, which is 33.8 BTU per pound mass, and we will have our value 37 times 33.8, 1250.6. Cancelled pound mass, BTU per second. And converting BTU, since we are solving our work in horsepower, so I'm converting BTU into foot-pound force. So 778 foot-pound force, 1 BTU. And then converting foot-pound force into horsepower, 1 horsepower, 550 foot-pound force per second. Just like that, cancel BTU, cancel foot-pound force per second. We are left with HP. So U1 minus U2 is equivalent to 1250.6 times 778, and dividing the answer by 550. So change in internal energy, U1 minus U2 is 1769.0305 horsepower. That's it. Now we are going to solve for our flow work 1. So flow work 1 is equivalent to pressure 1 times volume 1. We already have our pressure is given and our volume is given, so we just have to substitute the given values. So pressure 1 is 15 pound force per inches squared. Then our volume 1 is 500 cubic feet of air. So that's already given. So 500 cubic feet per second. And then converting inches squared to foot squared. So 144 inches squared here, 1 foot squared at the bottom. So we will have cancelling feet squared by this unit, so we'll be left with foot-pound force per second. Converting the foot-pound force per second to horsepower, 1 horsepower will have 550 foot-pound force per second. Alright, just like that. So we will have a value of our EF1 as we multiply 15 by 500 by 144, then dividing it by 550. It is 1963.6364, 1963.6364 horsepower. Then next is we solve for our EF2, but in order for us to solve for EF2, we need to solve for our volume 2 first, and I'm just gonna put it here at this side. So our volume 2 is equivalent to, since density is mass over volume, therefore volume is equivalent to mass over density. Mass 2 all over density 2. So volume 2 is equivalent to our mass is given as, is already solved, 37 pound mass per second. Then dividing this one by our density, it's 2, which is also given, 0.304 pound mass per cubic feet. And then pound mass gets cancelled and cubic feet goes to the top. So volume 2 is equivalent to 37 divided by 0.304. Our answer is 121.71 cubic feet per second. So let me just confirm that. 0.304. So 121.710 cubic feet per second. So I'll be using that one in solving for my EF2, which is my pressure 2 times volume 2 is equivalent to, pressure 2 is 80 pound force per inches squared, and then multiplying it with my velocity, my volume, which is 121.7105 cubic feet per second, and then inches squared, converting that 144 inches squared all over 1 foot squared, cancel inches squared, foot squared cancel, or foot or feet squared cancel this one, the cube. So we'll be left with the unit of foot-pound force per second, converting foot-pound force per second to horsepower. So 1 horsepower will have 550 foot-pound force per second. Now we can cancel foot-pound force per second and we'll be left with the unit of horsepower. So flow work 2 is equivalent to 80 times 121.7105 times 144 divided by 550. So resulting value would be 2,549.2817 horsepower. That's for our flow work 2. We already have our flow work 1, flow work 2, internal energy 1 and 2. Now let's do this one at the back. Let me just do it here at the another paper. So our heat is equivalent to mass times the specific heat added. The specific heat added is already given, which is negative 13 BTU per pound mass, and we just need to multiply it by our mass. So in solving for our actual heat, we need to multiply it by mass. So 37 pound mass per second multiply it by negative 13 BTU per pound mass, cancel pound mass, BTU per second, converting BTU per second into foot-pound force. So 778 foot-pound force all over 1 BTU, and then cancel BTU, foot-pound force per second. Now we'll be converting foot-pound force per second to HP, so 1 HP, 550 foot-pound force per second. So cancel foot-pound force per second, we'll be left with HP. So our Q, our heat added or heat rejected, is now, I mean, it's not heat added but heat rejected because this is through cooling. So our heat rejected is 37 times negative 13 times 778 divided by 550. So it is negative 680.3964 horsepower. So all the values are all the variables are all these are solved. So we can now solve for our work. Work is equivalent to our general equation here, U1 minus U2 plus EF1 minus EF2 plus Q. So substituting the arrived values for those variables. So U1 minus U2 is 1769.0305, and then our EF1 is 1963.6364, and our EF2 is 2549.2817, and our heat is negative 680.3964. So mechanical work is 1769.0305 plus 1963.6364 minus 2549.2817 minus 680.3964. So our work in horsepower, work, since this is positive, so that means it's work produced. Work produced is 502.9888 horsepower. So this is the answer for our problem number 2.